that button now.
Hi, everyone. My name is Joe Evinger, and welcome to the Ashby Village Science and Ideas Group. Uh, I help coordinate this group's events with the help of our co-host and tech expert, Hillary Naylor and Sarah Evinger, who will soon introduce today's speaker. All of our members here are interested in science and education, but have various work experience backgrounds. We have over 70 members in our group and another 100 people or so that we include on our guest list. We meet via Zoom many Thursdays, the second Thursday of some months, I should say. We have a different guest speaker each month, speak to us on anything to do with science and ideas. Today we're going to talk about fire. Sarah will give more information later. Our next meeting will be in October. Dr. John Schwartzberg has been kind enough to come back and speak to us again of what's going on in the world of immunology and CDC vaccination guidelines and the rise of measles cases and renewed discussion of vaccines for diseases such as Lyme. We rely on our members to help us find speakers. If you personally know anyone who might present to us, please introduce them to me via an email. We're a 501c3, so all donations are accepted and welcome. And finally, uh, for our guest, if you are interested in Ashby Village, check out our website. Sarah will now introduce today's speaker, Jim Gasperini.
It is a pleasure to welcome back today's speaker who spoke to us a while back about this topic of fire. Jim is preparing for publication of a cultural history of fire, currently entitled Fire in the Imagination From the Burning Bush to Burning Man. A graduate of Williams College, he served as vice president of the Institute for Historical Study and Association of Independent Scholars. And during his eclectic career, his creative work is focused on the entertaining presentation of complex information to general audiences using various media. He has designed award-winning educational computer games, including Hidden Agenda, a simulation of Central American politics, and SimCity 3000, the third version of the best-selling urban planning simulation. Longtime participation in the Burning Man Festival and fascination with the use of fire as a spiritual practice have inspired his passion for the subject. Welcome back, Jim. It's all yours.
Well, thank you, Sarah and Joe. And let me share my screen. And there we go. And start the slideshow. Okay, continue to share. All right. So today I'd like to trace the long history of attempts to answer an elementary question, play on words very much intended. What is fire? Let's see. Many concepts that seem obvious to primary school students today were not at all obvious to our ancestors. Take the nature of air, for example. We feel its effects when the wind blows, yet we cannot see it. We constantly breathe it in and breathe it out and know that if we were to stop doing so, we would die. Usually we feel it as a single invisible thing, but at times vaporous water, smells, and sooty bits of earth float around in it. What is air? A flame leaps up for an instant, then disappears. A drop from a stirring spoon falling on the burner vanishes with a hiss. If we stop putting wood on a fire, soon its flames cease their flickering. Embers glow for a time, then one by one turn gray until all that remains is ash. Where is the fire gone? Where did it come from? If we strike certain rocks against each other, we can create sparks and make the fire appear again. Where was it until then? What is fire? Okay. Just way down here. All right. So implicit in the question, what is fire, is the larger question, what is matter? One classic answer arose independently in many cultures around the world. It proposes that matter is made up of a small number of elementary substances, one of which is fire. But then what are these elements? Thinking varied widely about the nature of the elements and how they comprise the material universe. Philosophers pondered such questions as, does matter exist eternally, or can it be created and destroyed? Are the substances we perceive real, or the manifestation of underlying forms or principles? Are the elements continuous, or composed of tiny, invisible particles? Through centuries of such debate, fire was long assumed to be an element, co-equal with air, water, earth, and sometimes others. The first among the Greek philosophers, Empedocles first articulated the idea that everything in the universe is made up of four roots, as he called them, and that the competition between these four explained the structure of the world. He named them for four Greek gods, but in context he clearly meant earth, water, air, and fire. Humans experience the various mixtures formed by their competition as different substances. For example, bone, according to Empedocles, consists of 2 parts earth, 2 parts water, and 4 parts fire, while flesh and blood contain an equal mixture of of the 4 roots. Empedocles was perhaps too close an observer of nature. His famous demise in the volcano inspired the classic doggerel, "Great Empedocles, that ardent soul, leapt into Etna and was roasted whole." And that's a picture, a painting of him doing that on the right. Some claim that he thought he was going to prove that he was a god, but his sandal came flying back out, and that proved that he wasn't. Plato, born just after Empedocles died, called these roots elements, a term that stuck and formed the basis for Western natural philosophy for the next 2,000 years. Similar lists of elements or first principles appeared in the natural philosophies of Persia, India, Tibet, China, Japan, and North America, sometimes paralleling the Greeks, but with significant variations. In some traditions, the elements get created in a specific sequence. In Zoroastrian cosmogony, for example, the supreme god Ahura Mazda created the universe in 7 stages. He first created sky or air, then water, earth, plants, animals, and human beings. All 6 lay inert until the 7th element, fire, which serves as the life force animating the world, was created. Japanese tradition specifies a list of 5 great elements: earth, water, fire, wind, and void, or sky. Sometimes consciousness gets added as a 6th immaterial element. Ka, fire, is the main constituent of energetic, moving, forceful parts of the world, including animals and things that destroy. The 5 tapering layers of stone lanterns in Japanese temples and Zen gardens represent the 5 great elements. In the middle sits the fire layer, obviously because it's a lantern that's in the middle, supported by a bottom layer for earth, then one for water, sometimes represented by a lotus flower, and above the entire central fire layer, layers representing wind and sky gesture upward. Buddhist conceptions of the 4, sometimes 5 great elements also exhibit great variety. Over the centuries, Buddhist philosophers wrestled with complex ideas about the material world we experience through our senses. Is what we perceive real, or the surface reflection of deeper great essentials, or the completely illusory product of our minds? In early Buddhist texts, earth, water, air, and fire were said to be our sensory experiences of more abstract underlying principles: solidity, fluidity, mobility, and heat. Fire consists mostly of heat, though, like every perceptible phenomenon, it contains a mixture of the four principles. Matter is only our mental interpretation of what we can perceive of the true elements through our senses. The colors of Tibetan prayer flags symbolize the five elements as we perceive them: yellow for earth, green for water, red for fire, white for air, and blue for sky. Some cultures link the elements with various other phenomena that can be grouped into short lists, such as the seasons, the cardinal directions, and the planets. In one such complex system of correspondences, the Chinese Wuqing, short for the five types of qi dominating at different times, elements consist of cycling phases in continual transition. Each phase gets generated by another phase. Fire reduces water to ashes, which become earth, from which we derive metal. Metal accumulates water, which nourishes wood, which provides fuel for fire, completing the cycle. At the same time, each phase controls or overcomes another. Fire controls metal, since only with fire can metal be melted or forged. Water controls fire, since it can put fire out. No phase is stronger than any other. Each has its place and function in the eternal chain of life. The one classical Greek element missing from the system of mutual relationships, air, is sometimes identified as the primal qi, the life force underlying all. The five phases pervade many phenomena in traditional Chinese thinking. Each phase corresponds with a planet. The one for fire is Mars. Fire also associates with the direction south, the color red, the summer season, the heart, among the major organs of the body, and the vermilion bird, one of four constellations with symbolic significance, also known as the four auspicious beasts. It has a positive or active yang aspect manifested in wildfires or volcanic eruptions, and a negative or passive yin aspect, which can be brought to serve our needs in the light of a lamp or the warmth of a hearth. The difference between the yin and yang aspects of fire is not great. A campfire, for example, can easily get out of control and burn down the forest. Some North American indigenous peoples associate the four elements with the cardinal directions, north, east, south, and west, and other phenomena, including stages of life, birth, youth, adult, death, the seasons of the year, and directional winds. In ceremonies, the activating spirits of the elements and directions may be addressed with the respect due living beings and honored for their roles in sustaining life. Many modern pagans also honor the elements along with the directions in their rituals, considering them animate beings. A Manual for Witches by Anna Mura, who also goes by the name of Ayumiel, details ceremonies for the full moon, dedications, and important dates in the Wiccan calendar. A ceremony begins with casting the circle, laying out a circle with rope or drawing one in the dirt, then placing candles at the four directions. The practitioner lights each of these candles with an altar candle and addresses the direction personally. For the southern candle, she says, "I call upon light and fire at the south to illuminate and warm the circle." Later in the ceremony, she raises her wand and says, "I call upon you, elemental fire, to tend this rite and guard this circle, for as I consume life to live, we are kith and kin." At the end, the practitioner snuffs the candle of each elemental power in turn and invites it to depart in peace with her blessings. Mura explains her understanding of the elements as follows. The four elementals are more than personifications of earth, air, fire, and water, more than the symbols of colors, directions, seasons, and aspects. They are the real entities of powers that the practitioner can evoke for assistance. There are those who see the elementals as unknowable forces without personality, as a what? My view is that since I am made up of parts of them and I am a who, so are they. I call them my kith and kin. Earth is my body, air moves my breath and stirs my intellect. Fire is the spark of energy within me, my passion, and water is my bodily liquids and my emotions. Some of the earliest Greek philosophers also thought of fire as a fundamental force. For Heraclitus, everything is fire. This world was not made by any god or man. It always was and will be an ever-living fire. Parts of it kindling while other parts go out. Heraclitus compared the role of fire in the universe with the role of money in the marketplace. All things are exchanged for fire, and fire for all things, even as wares for gold and gold for wares. Philosophers of the Stoic school, which flourished from the 3rd century BCE to the 3rd century of the Common Era, held a similar view, except that for them, a designing fire, quote unquote, creates and destroys all things with purposeful intelligence. Nature is an artistically working fire, a fiery, creative, or fashioning breath. Greek philosophers came up with several other theories about the fundamental building blocks of the universe. The atomists, beginning with Democritus and Leucippus in the 5th century BCE, reasoned that if you cut a piece of matter in half, you still have the same type of matter. If you then cut it in half again and do this over and over, you still have the same matter. There must be a point, however, where you can't divide something anymore and have reached the smallest possible piece of it. They called these hypothetical tiny particles atoms, which literally means uncuttables. Opinions varied about how the nature of atoms and their relationship with their elements. 2 principles underlie the world, said early atomists, atoms and void. Tiny, immutable atoms come in an infinite number of shapes and sizes. They wander through surrounding void until they collide with others and clump together. Their surfaces have tiny barbs and hooks like Velcro. We experience these entangled atoms clustered together in many positions and arrangements as material substances. Opinions varied on such questions as to whether atoms are infinitely small or of finite dimensions, whether the 4 elements are each made from a different kind of atom or from the same universal substance, whether or not atoms can change from one element into another, and whether atoms are hollow or solid. The idea that the world could be made of very tiny particles occurs in the natural philosophies of many traditions, including the Vaisheshika school of Hinduism and Theravada vehicle of Buddhism. One Buddhist text poetically specifies that an atom, a puru manu, is the size of 1/4096th part of a minute particle of dust seen dancing in the sunbeam. That's beautiful. Plato argued for a type of atomism based on mathematics, specifically geometry. Everything we perceive is made of tiny geometric shapes, he thought, comprised of 7 and even tinier triangles. Each of the 4 elements has a different shape. The earth element shape is a cube made of isosceles triangles, 2 sides the same length. The other 3 elements are made of equilateral triangles. Fire shapes have 4 tetrahedrons, air shapes 8 octahedrons, and water shapes 20 icosahedrons. These shapes continually jostle and mix, aggregating into compounds that we perceive as continuous flows of air and water, clumps of earth, and flames of fire. When fire, air, and water shapes collide, their component triangles can break loose and rearrange into shapes of a different element. Earth shapes made of a different kind of triangle do not participate in these transformations. The small pyramidal fire shapes have sharp edges and points that cut into clumps of other shapes, splitting them apart. We perceive this action of massed fire shapes as burning. When external fire shapes come near us, we feel the sharpness of their triangular edges as heat. In Plato's theory of digestion, the sharp angles of fire atoms enable them to penetrate and break up the larger earth and water items that make up food. The new fire items of young people have sharp triangles that easily slice into reusable pieces like the older and feebler triangles making up atoms of food and drink. Alas, as people grow older, the triangles of their internal fire atoms become blunted with long use, dulling their ability to penetrate and cut. They can no longer easily break up particles of food. Eventually, they degrade to the point where incoming food atoms break them up instead. The body becomes enfeebled and wastes away. This condition is termed old age, quote unquote. Finally, when the triangles comprising the marrow snap asunder with the stress, the bonds loosen and that attach the soul to the body, and she flies away with gladness. Love of poetry in the ancient philosophers. Plato's pupil Aristotle rejected the idea of atoms, asking such questions as, how do we know that these invisible things really exist? What are they made of? Why should a process of cutting things into smaller and smaller pieces stop at a particular point? He denied the possibility of voids, arguing that the existence of a void would mean that what is not exists, an absurdity. Nature abhors a vacuum, he wrote. But if there is no space between particles of matter, countered the atomists, how do they move and rearrange as they obviously must? Aristotle proposed that the four terrestrial elements are continuous compounds of basic sensory qualities: hot, cold, wet, and dry. Fire is mostly hot, but also dry. Its opposite, water, is cold and moist. Elements can transform into other elements. For example, the sun's rays convert cold, moist water into hot, moist air. In similar fashion, cold, dry earth can transform into the smoky exhalations of hot, dry fire. Flames and lightning display these hot, smoky exhalations at the boil. Though the fiery exhalations naturally tend to rise and join the ring of fire surrounding the world above the atmosphere, they can also get swept up into powerful winds that flow like rivers through the air, slamming into the earth and causing earthquakes. Despite the predominant influence of Aristotle's thinking in both the ancient and medieval worlds, some schools of philosophy continued to promote versions of atomism, notably the Epicureans. The Roman Epicurean Lucretius, mid-first century BCE, described minuscule, indestructible atoms moving constantly at enormous speed, bouncing off each other. Despite their rapid motion, they are so small that we see groups of them at the macroscopic level as motionless or moving slowly. He rejected the limitations of the four-element system, proposing instead a variety of atomic shapes. The different proportion of perceptible macroscopic substances are determined by properties of their component atoms. For example, things that feel smooth are made of atoms round like poppy seeds, while briny things mix smooth atoms with rougher oblong ones. Fire atoms come fanged with teeth that prick the senses of the body. Until a piece of wood kindles, fire atoms lie interspersed among the other atoms like seeds of potential fire. Visible fire consists of fierce streams of fire atoms, briefly seen dancing together as tongues of flame. Unable to unite into something fixed, they quickly disperse into the chaotic air. Lucretius rejected the idea that an actual fire element lurked in the wood. If that was the case, Wouldn't the chopping action of an axe set it free? He still held to the notion, however, that when something burns, a fire principle or particle escapes into the air. But in recognizing fire as a potentiality in an unkindled log rather than an actual fire element, he came closer than anyone would come until the late 18th century to the modern conception of combustion. The debate over the nature and existence of atoms fell quiet early in the Common Era. The idea would smolder, nearly forgotten for over 1,000 years, then flare up again with the revival of interest in Greek thought during the Renaissance. Atomists had no monopoly on ideas about the nature of fire and the other elements. Speculation about the constituent components of the world continued throughout the primacy of alchemy and into the scientific era. Alchemy, a branch of natural philosophy also practiced in India, China, and the Muslim world, in its Western form, began in Egypt in the early centuries of the Common Era. Though detractors later characterized alchemists as secretive mystics slowly obsessed with turning other metals into gold, they pioneered many innovations in laboratory techniques, metallurgy, medicine, and chemical analysis, setting the stage for the scientific revolution. Some of the most important early scientists were alchemists, including Isaac Newton, astronomer Tycho Brahe, and Robert Boyle, the first modern chemist. The insistence of modern science on rigorous quantitative experimentalism and skepticism of ancient mystical wisdom caused a break with alchemy in the early 18th century. Alchemy went into steep decline, though it never entirely went away. Looking beyond the surface attributes of fire, alchemists sought a principle of combustibility, which they identified with a philosophical version of sulfur. In the mercury-sulfur theory of metals, attributed to influential 9th century Islamic alchemist Jabir ibn Hayyan, known in the West as Jibir, the world was primarily made of philosophical mercury, so named because mercury, or quicksilver, is the closest approximation to the underlying principle of volatility. Interacting with this philosophical mercury is philosophical sulfur, also named for a visible substance long known to the ancients. Sulfur, or brimstone, had long been associated with fire due to its yellow color, easy flammability, and the sulfurous odor that sometimes accompanies lightning. Sulfur and mercury are both elements by the modern use of the term, but just two among many. But how could principles of volatility and combustibility form anything solid, visible, or persistent? The influential Swiss alchemist Paracelsus addressed this problem by adding a third primary element, salt, which he thought to be the closest earthly approximation of the principle fixity. Thus, idealized mercury, sulfur, and salt became the new primary elements. The old Aristotelian four of earth, air, water, and fire were considered subordinates derived from the new tria prima, or three primes. When a log burns, according to Paracelsus, the salt in it becomes ashes, its mercury evaporates, and its sulfur gets consumed in the flames. Aristotelians used the same example of burning green wood as evidence instead for the traditional four elements. Robert Boyle summarized their positions in The Skeptical Chemist, 1661. Fire is evident in the flame. The vanishing of smoke into air manifests to what element it belongs and gladly returns. The boiling and hissing on the ends of a green log portray the presence of water, and the weight and dryness of the ashes put it past doubt that they belong to the element of earth. Throughout the 17th century, alchemists and Aristotelians carried on a lively and often acrimonious debate. Some tried to reconcile the three alchemical elements with the Aristotelian four. After a time, earth regained its status as a primary element, then water. In 1584, the English Paracelsian Thomas Moffat complained about the multiplicity of systems. Some wish that there should be but one element, while others think that there are many, and some even think that they are infinite, innumerable, and immovable. These assert there are two, those three, some others say four, while others still demand eight. It seemed possible for a time to prove the existence of a fire element by distilling it from an unlikely source. So claimed the German alchemist Hennig Brand, who spent the fortunes of two wealthy wives in a search for the elusive philosopher's stone that could unlock the secrets of the immortality and turn other metals into silver and gold. In a 1669 experiment, he distilled prodigious amounts of urine. At the end of the process, a mysterious liquid dribbled out of his apparatus. It seemed to gleam with vital force and spontaneously burst into flame unless cooled. Concluding that he had distilled the element fire, he sold the recipe to a chemist named Kraft, who demonstrated the marvelous self-igniting substance all over Europe. The secret of how to make it leaked out, as it were, and soon early scientists such as Robert Boyle experimented with it as well. Brandt, however, likely brought to public knowledge what was by then a century-old secret alchemical formula. Paracelsus included a recipe for how to distill the element of fire, very similar to Brandt's, in a manual of hermetical medicine. Take urine and thoroughly distill it. Water, air, and earth will ascend together, but the fire remains at the bottom. After the fourth distillation, receive the air and the fire in a separate vessel, which put in a cold place, and there will be concealed certain icicles, which are the elements of fire. Such distillation can indeed produce not elementary fire, but phosphorus, an element by the modern definition which self-ignites when exposed to air at about 86 degrees Fahrenheit. Mysterious conflagrations blamed on witches and demons may have been caused by arsonists who bought phosphorus from unscrupulous alchemists. A century after Brand's discovery, quote unquote, the experiments with burning phosphorus would play an important role in solving the riddle of combustion. Natural philosophers long noted a special relationship between fire, air, and life. Ideas for how this relationship worked flowed back and forth over the centuries. The Stoics conceived of an active vital force that they called pneuma, a combination of fire and air like a fiery breath. This fiery, creative, designing breath generates all form and motion in the material world, shaping and holding bodies of matter together. It burns on the spiritual level as well, giving animals their life functions, animating their souls, and enabling reasoning animals to think, plan, and make decisions. Others proposed that the air contained some sort of food for fire. This would explain why a candle placed under an airtight jar will soon go out. Without a fresh source of air, the candle will use up all the aerial food. This fire food, pabulum ignis, or haunter in the air, must be something other than the wax and wick, since the candle burns normally until placed under the jar. Much like a candle, an animal placed under a jar will cease to breathe and go out. Why? Paracelsus reasoned that since we die if we cease to breathe, a vital life flame, flamma vitalis, must permeate the air. The Irish philosopher George Berkeley described air as a mass of various particles permeating the air by animating force of pure invisible fire, the animal spirit of the visible world. Some identified this vital flame with the philosophical element sulfur. Others thought fire to consist of minute sparks struck from collisions between particles of sulfur and niter, plus potassium nitrate, another substance thought to permeate the air. Paracelsians proposed that both sulfur and niter, the active ingredients of gunpowder, flow from the stars. Some stars exhale sulfur, while others give off niter, When these emanations mix, this gunpowder in the air can explode, producing thunder and lightning. Other proposals envisioned an inverse of this cosmic respiratory system. Fiery exhalations rising from the surface of the Earth feed the stars, comets, and sun. The French naturalist Jean-Baptiste Robinet proposed that sunspots result from smoky exhalations attracted to the solar surface. In time, he warned in De la Nature from 1766, the sun may absorb so much of this material that its light will go out. But as Gaston Bachelard commented dryly, the stomachal rhythm of the universe must be very powerful indeed if the Sun King will die from overeating. Though we have much to concern us about the effects of our own smoky exhalations on the planetary climate, at least we need not worry about extinguishing the sun. From ancient times, people knew to fear air somehow gone bad. Suffocating or poisonous vapors often found lurking in confined spaces. The Romans lowered lamps into caves and mines before entering, watching to see if they continued to burn to avoid mysterious suffocating miasmas. Caged canaries served the same purpose in later centuries. Studying these vapors, the Dutch chemist and physician Jean-Baptiste van Helmont, who lived from 1580 to 1644, isolated a substance emitted when charcoal and alcohol burn. He then found the same substance discharged when beer and wine ferment and when vinegar mixes with the shells of crabs. He called it a gas, from the Greek word chaos. We now call the gas he studied carbon dioxide. Later scientists isolated other invisible gaseous substances, calling them variously factitious airs, modified airs, aerial acids, or elastic fluids. Combining oil of vitriol, sulfuric acid, with iron nails produced flammable air, later known as hydrogen. The combination of aqua fortis, nitric acid, with oyster shells liberated a fixed air that was not flammable, which we now know as nitrogen. Were the airs produced by these procedures modifications of the element air, or foreign substances dispersed within it? Or was the atmosphere just a receptacle for airs of different sorts? It took many years of experimentation for the properties of the different types of air to be sorted out, appropriate names agreed upon, and theories developed to explain their differences. Von Helmont's coinage gas eventually won out as the general term for airs of different kinds. As early scientists performed experiments trying to explain fire, they were on the right track in suspecting that some segment or constituent of air enables flames to burn and bodies to respire. For some decades, however, attention shifted from the mystery of the vivifying spirits in the air to interpretations of combustion as a mechanical process. People have long looked for keys to the secrets of the universe by studying their own inventions. The Western world was still exploring the uses of the Chinese invention, gunpowder, when alchemists hypothesized that lightning, flames, and the heat of the body could all be explained by explosive interactions of sulfur and niter. In recent times, the idea that the universe might be a vast computer simulation has had its vogue. During the scientific revolution of the 16th through 18th centuries, many proposed that the world might be a vast machine. Among the most influential ideas prompted by the rediscovery of ancient Greek and Roman texts during the Renaissance was the atomist conjecture that the world might be composed of tiny particles. At a time when mechanical devices such as clocks were becoming increasingly sophisticated, the workings of tiny moving cogs and intricate clockworks suggested an analogy with tiny moving bits of nature. Mechanist philosophers speculated nature might consist of a vastly complicated machine composed of discrete interacting parts. Some claim that this watchmaker analogy proved the existence of God, who set the machine in motion and may still be directing its movements. By understanding the way the machine works, they hope to better understand the mind of the Lord. Others thought that the world could work like a machine, but without guidance by a divine hand. Making a methodical study of the various sources of heat, the English natural philosopher and statesman Francis Bacon, who lived from 1561 to 1626, determined that their common element is rapid motion, as exemplified by the constant flickering of flames and the roiling of hot liquids. He reasoned that heat is not a property inherent in a fire element or driven by a vital spirit, but produced by the movement of small particles of matter interacting mechanically. Galileo Galilei took a similar position. Quote, "Those materials which produce heat in us and make us feel warmth, which are known by the general name of fire, would then be a multitude of minute particles having certain shapes and moving with certain velocities. Meeting with our bodies, they penetrate by means of their extreme subtlety, and their touch, as felt by us when they pass through our substance, is a sensation we call heat." Unquote. Bacon and Galileo both figured prominently in the development of the scientific method. Bacon went beyond the ancient practice of close observation of nature by systematically comparing different sources of heat and light, analyzing what they had in common and what they did not, and using inductive reasoning to explain his empirical observations. To fully answer the difficult question, what is fire, required, however, the development of more advanced techniques of experimentation. The invention of more sophisticated equipment, typified by Galileo's experience with a telescope, spurred these more sophisticated techniques. The increased refinement of tools and techniques did not, of course, guarantee accurate interpretation of the data produced. Robinet, for example, believed that fire consists of igneous beings that grow from germs like plants and animals, have natural lifespans, grow old and sterile, then in time die, even if well fed. After striking a flint over a sheet of paper through a microscope, he observed charred specks and some round and shiny atoms, although the naked eye could see nothing. They were little shiny worms. Though natural philosophers sometimes drifted in circles around the problem of fire, discarding certain ideas only to revive them decades or centuries later, they gradually spiraled closer to a solution. Along the way, they sometimes spun off into strange side currents. This is the Cartesians is probably the hardest thing for me in doing all my research to try to grasp. The eminent French philosopher René Descartes, from 1596 to 1650, took a purely mechanistic view of the universe, rejecting ideas of animate or divine direction expressed through a vital force. He also rejected the almost atomist notion of voids between particles. He and his followers recognized only three elementary substances: fire, air, and earth. They considered water secondary. All three, they thought, are composed of corpuscles, particles similar to atoms but capable of further division to smaller parts. Whenever a corpuscle moves, another slides into place from behind. Meanwhile, a third slides in behind the second, and so on. Strings of corpuscles tend to move in circular patterns, forming vortexes. These circular patterns of movement occur on many levels. A pattern of immense vortexes explains the circular movement of the planets. The Cartesian Nicolas Malebranche specified that the subtle or ethereal matter is composed of an infinity of small whirlpools that turn on their balance. When the equilibrium breaks, the phenomenon of combustion, of lightning, of the bursting of the gunpowder occur. According to the Cartesians, fire corpuscles, the smallest and most fluid of the elements, can change shape and size and break apart to fill any pores or crevices that might threaten to open between clusters of larger corpuscles. The rapid movement of fire corpuscles creates heat. Merely by rubbing our hands together, we heat them, Descartes observed, and any other body can also be heated without and any other body can also be heated without being placed close to a fire, provided only that it is shaken and rubbed in such a way that many of its small parts are moved. Contrary to Aristotle, he thought that fire particles do not naturally rise to a sphere of fire around the globe, but move in every direction, which can be directly seen in the flickering of a flame. They tend to move upward only because they follow the path of least resistance, pushed by the pressure of the larger and more stable particles. So, the influential Dutch chemist and physician Helmont thought of fire as an omnipresent, elusive, but pervasive, subtle matter. Minute fire particles exist everywhere, penetrating the pores and interstices of even the most solid gold, as well as the most empty vacuum of an air pump. Instead of the deformable and breakable corpuscles of Descartes, his fire items are corporeal, solid, spherical, and immutable in size and shape. They are not, however, subject to gravity. Fire atoms repel each other and try to expand, providing the impetus for action and movement in the world. This pure fire serves as God's instrument for effecting an action and movement in the world. The pure fire serves as God's instrument. It gives us air its elasticity. When ignited by friction, the parallel rays of the sun, or a spark of vulgar fire, fire particles can break the bonds of attraction that keep clusters of Earth's atoms together. The clusters burst apart, and the fire atoms shoot forth as the heat and light of flame. Though Boerhaave's was a mechanical vision like that of the Cartesians, his conception of solid atoms attracting and repelling each other drew from the increasingly influential theory of invisible forces central to the thought of his English contemporary Isaac Newton. Against the objection of the Cartesians, who considered the concept of forces acting between distant objects a preposterous revival of ancient animist ideas, Newton's principle of gravitational attraction steadily gained precedence as their superior explanatory power became apparent. Leading scientists long persisted in the mistaken conviction that the energetic action of fire consists of flammable substances rapidly splitting apart. That is what combustion looks like, after all. When a log burns, it dismembers. We can see with our eyes, wrote Descartes, that when flame burns wood, it moves the small parts of the wood and separates them from one another. The disruptive power of fire alone will be able to cause in the wood all the same changes that one experiences when it burns. It took centuries for a counterintuitive idea to take hold. Combustion actually consists of things combining in chemical reactions. A step towards understanding the importance of chemical combination came from the German alchemist and physician Johann Joachim Becher. In 1667, he imagined the existence of a sulfurous or oily principle mixed into various substances in different proportions, which his student George Stahl named phlogiston, from the Greek phlogistos, burnt or inflammable. Phlogiston, they thought, can be found mixed into all flammable substances. When something burns, the phlogiston particles it contains vaporize. When its phlogiston finishes burning off, combustion stops. Vaporized phlogiston spreads through the air until absorbed by plants, then gets passed into animals and minerals, and the cycle turns again. Though much of phlogistic theory amounted to old sulfurous wine in a new bell jar, it plausibly fit the known data, offered a useful solution to a complex problem, and dominated chemistry for decades. In the second half of the 18th century, however, researchers performed experiments that called into question its very existence. In the 1770s, the pace of scientific advance had picked up as a small group of competing researchers in several European countries addressed the problem of explaining fire. As chemists and natural philosophers, the term scientist did not come into use until the 1830s, came closer to solving the enigma of fire, intense rivalries underlay the collegial correspondence and sharing of results between members of the Royal Society of London for Improving Natural Knowledge and the Paris Académie des Sciences. Although many researchers contributed to the exciting developments, the principal figures were the English chemist, theologian, and political theorist Joseph Priestley and the Swedish pharmacist Carl William Scheele, each of whom discovered oxygen independently, and the French chemist Antoine Laurent de Lavoisier, who identified oxygen's role in combustion. Priestley had a noble patron who supported his work, though not lavishly. Lavoisier, a nobleman himself, used his powerful position in the French aristocracy to provide himself with the finest laboratory equipment available. When Scheele wasn't running a pharmacy business in the small town of Köpings, Sweden, he was able to borrow a friend's modest laboratory in nearby Uppsala. All three begin with. Crucial advances in the scientific understanding of fire came from the study of a special kind of combustion, the calcification or calcination of minerals and metals. Certain metals will, when heated to the point of burning, transform into a crumbly powder known as, at the time, as a calx, now known as an oxide. Mysteriously, when metals become calxes, they get augmented. They weigh more after burning than they did before. But if the process of burning releases fire particles from something burned, as has always been assumed, shouldn't what remains weigh less? The process of burning wood was hard to measure with instruments of the time, what with the smoke, ash, heat, and vaporized moisture all going in different directions. The simpler calcination of metals offered a way to experiment with more precision. Researchers conducted experiments using inflatable bladders, air compressors, vacuum pumps, piston and valve instruments, glass and copper globes and tubes, swan-necked glass retorts, tobacco pipes, bell jars, pneumatic troughs, pneumatic shelves, bottles partly filled with water or mercury, receiving vessels suspended from wires, gas cylinders, glass lenses, precision scales, and ox bladders. They executed tests using iron wire, lead, copper, brass, tin, phosphorus, manganese, mercury, the calxes of all these metals, pyrite, saltpeter, silver carbonate, various nitrate salts, and many types of acid. For heat, they tried candle flames, smoldering charcoal, and the rays of the sun, focused through a burning glass. Living near a brewery in Leeds, where vast amounts of vats fermenting barley wort produced great quantities of fixed air, carbon dioxide, Priestley experimented with impregnating bottled water with it, hoping to invent a cure for scurvy or cancerous ulcers. The bubbly product did not pan out as medicine, but in the process, he invented carbonated water. He could have made a fortune on this discovery, but in the process, as a Swiss scientist named Schweppes promptly did. But among Priestley's many theological, philosophical, and political pursuits, making money was never a priority. And then isolated other airs, including nitrogen, carbon monoxide, and sulfur dioxide, though his analysis of what he had produced had many flaws. In August 1774, he isolated a surprising new air. Heating the calx of mercury seemed to remove phlogiston from the air and put it back into the metal, leaving the remaining air dephlogisticated. Candles burning brightly in this new air, and animals breathed very freely. Testing it on himself, he found it 5 or 6 times better than common air. Following a reverse process, burning a metal into a calx or a candle in an enclosed space, he observed that the confined air killed candles and mice alike. He called this phlogisticated air. Today we call the depleted phlogisticated air nitrogen and the nourishing dephlogisticated air oxygen. A little before Priestley began this work, Scheele determined that phosphorus burned readily in what he called fire air, oxygen, but not at all in vitiated air, nitrogen. He determined that the two airs comprised most of the common atmosphere, measuring their relative proportion with reasonable accuracy. Interpreting these results in logistic theory, he proposed that fire air, the elastic minor constituent fluid of the atmosphere, eagerly attracts phlogiston, while the merry major constituent does not. His conclusions partially anticipated those of Lavoisier, except that Lavoisier, armed with information from Priestley, was soon to abandon phlogiston altogether, and in so doing, revolutionize chemistry. On a visit to Paris in October 1774, Priestley demonstrated his surprising discovery of dephlogisticated air to Lavoisier and other assembled savants. Lavoisier quickly duplicated Priestley's work and recognized the significance of the discovery better than either Priestley or Scheele. A famous experiment in 1777 clinched the question for Lavoisier. It focused again on the calcination of mercury, a metal with unique properties. At a gentle boiling temperature, liquid mercury combines with oxygen to produce a red calx, or oxide. If this calx then gets heated a little more, the mercury gives off the oxygen again and precipitates back into liquid form. Lavoisier managed to do this back and forth in an enclosed space without using charcoal, a possible contaminant. He showed that when the mercury turns into a calx, the enclosed air becomes depleted. Then when the calx gets heated more and mercury precipitates out, the air returns to its original state. He had definitively proved that a burning metal combines with a part of atmospheric air to form a calx, and the weight of the air fixed in the calx accounts for its augmentation. The substance that Scheele called fire air and dephlogisticated air, Lavoisier renamed oxygen from the Greek term for acid generating. He declared that multiple types of air exist, that they are not modifications of common air but separate components, and that one of these elastic fluids, oxygen, was salubrious and kept flames and animals alive, while the other, nitrogen, was inert and extinguished them. He broke with phlogistic chemistry, declaring phlogiston to be an imaginary, unnecessary notion. In doing so, he chose an unpopular, counterintuitive theory, performed careful experiments to substantiate his ideas, and promoted the theory relentlessly despite initial opposition. At long last, a plausible, data-driven solution had been found to the ancient question, what is fire? Fire is the rapid oxidation of burnable substances, fuel, in a chemical process that releases heat, light, and other products. Lavoisier's work revolutionized chemistry and laid the groundwork for the modern scientists. Phlogiston, the last incarnation of the fire element, with the accumulated weight of millennia of mistaken thinking behind it, did not go down without a struggle. Advocates, including both Scheele and Priestley, continued to fight a losing battle to explain new data with some role for phlogiston. Their interpretations grew increasingly labored and complex. Phlogiston theory reversed modern understanding, interpreting the gain of oxygen in a burning substance as the loss of its phlogiston. According to one scholar, this inversion, quote, was in great part responsible for successful, if often complex and quaint, interpretations by phlogiston chemistry. An explanation and its virtual inverse may well be equally successful over some considerable runs of data, unquote. Eventually, phlogiston became remembered as a peculiar, outmoded idea that somehow hung on long after its days permeating the pores of the universe should have passed. Chemistry advanced rapidly in the decades following Lavoisier's big conceptual leap. Through years of experimentation and debate, researchers sorted out the differences between different flammable gases, including hydrogen, methane, and carbon monoxide. The discovery that water is a compound of a flammable air, hydrogen, and vital air, oxygen, brought down another of the Aristotelian four, confirming the revolutionary turn in the science of chemistry and cementing this change as one of the most important conceptual leaps of all time. The principal discoveries of oxygen and its role in combustion had become famous in varying degrees. Joseph Priestley led an extraordinarily varied and dramatic life. At one point, his support for the French Revolution and radical Unitarian religious ideas provoked an angry mob to burn down his house, laboratory, and church in Birmingham, England. He escaped to Philadelphia, where he lived into the 19th century, still holding a torch for phlogiston, his preferred theory of fire. Scheele, the least known, also discovered barium, manganese, molybdenum, numerous types of acid, chlorine bleach, and a method for mass-producing phosphorus that sparked the world-leading Swedish match industry. Many of his discoveries were long attributed to others, including that of oxygen. Though Scheele's work had actual precedents, both Priestley and Lavoisier published their results before he did. Alas, he did not live to see much of the fruits of his labors, dying in 1786 at the age of 43 from the cumulative effect of exposure to the many poisonous chemicals used in his experiments. In 1794, Antoine Laurent de Lavoisier lost his head to the guillotine, the Place de la Révolution in Paris, despite his stature as one of the greatest scientists France ever produced. He was not, however, just an innocent scientist, unfortunately swept up in revolutionary madness. To help pay for his aristocratic lifestyle and scientific research, he had a day job as administrator of the hated Ferme Générale, a tax farm operation that collected duties for the king. Notorious for the great wealth they amassed by charging large fees, the secrecy that shrouded their contracts, and the violence of the thugs they hired to enforce their operations, the fermier helped provoke the French Revolution. Beginning with John Dalton's work classifying elements by atomic weight in the early 19th century, the empirical methods of modern science confirmed a version of the metaphysical thesis of ancient atomists, that matter comprises minute particles of different types. The ancient terms atom and element, wildly varying concepts over the centuries, settled into two standard scientific definitions, or a standard definition. Over 100 elements are now thought to exist, distinguished by how many protons they contain. An atom is an individual instance of an element. Only in the last century have we learned how to split uncuttable atoms apart, unleashing the powerful energies of nuclear fission. It can be argued that Empedocles and the many others who struggled so long to squeeze the universe into a short list of 4 or so elements were onto something that not that distant from modern scientific understanding. The classical elements earth, water, and air roughly correspond to 3 states of matter: solid, liquid, and gas. Fire is the odd one out in this analogy, unless understood as the energy that transforms one state of matter into another. If hot enough, fire can actually produce a 4th state of matter, plasma. Created by the ionization of superheated gases, atoms stripped of their elements, plasma can be generated by lightning or an acetylene torch. It also floats inside the tubes of neon lights. While relatively rare on Earth, plasma is by far the most common state of matter in the universe, because the stars consist mostly of plasma. While considering stars, it may be worth digressing briefly from our focus on terrestrial fire to consider the term burning when used in a stellar context. While earthly combustion centers on oxidation, the process of combining other substances with oxygen on a molecular level, the energy of stars comes from fusing lighter atoms into heavier ones. Now, maybe I'll skip, in the interest of time, I've gone over an hour here, so I'm going to skip the rest of this discussion of what fire means in the context, or burning means in the context of stars. Once science figured out its chemistry, fire lost some of its importance in the imagination. Chemistry downgraded flame to an atomic reaction, says fire historian Stephen Pine. Fire shrank from Heraclitean universality to a laboratory demonstration. Once the manifestation of the deity and the source of life, fire had become alien, a destroyer of cities, a savager of soil, a befouler of ale, an emblem in science as in agriculture of the hopelessly primitive. And yet, as Gaston Bachelard reminds us, a slightly hypnotized fascination remains surprisingly constant in all who watch a fire. Many still prefer the warm glow of a candle or a fireplace to the more efficient and convenient but colder electrically powered luminescence, particularly when in a romantic or convivial mood. We still use fire for fun, lighting celebratory fires on occasions ranging from the solemn to the silly, and to signal serious intent when performing rituals and ceremonies. And although at long last we have begun to move away from it, our civilization still relies largely on burning stuff for our energy needs. Okay, so that's drawn from a chapter of my book, which I would appreciate your thoughts on the title. As Sarah mentioned at the beginning, it was long called Fire in the Imagination. Now we're thinking of Minds on Fire. And here we have Imagining Fire with the subtitles Minds on Fire, or the Mind on Fire, Fire in the Imagination, Fire in the Mind. Any thoughts you might have on the title, particularly on whether Minds on Fire tells the story adequately, I would appreciate it. So maybe I will stop sharing now, as long as I need to find my cursor. There we go. Okay.
Well, Jim, what you don't want to call it is you're fired. Or something like chemistry, romance, practicality. But I'm sure other listeners will have good suggestions.
Burning questions.
Mm.
Mm.
Do you have any burning questions? Or have I burnt you out?
Okay.
Audrey has a question. Audrey, unmute.
Audrey, you need to unmute.
Unmute.
Okay. There you go.
Sorry. In some of the 18th century discoveries, and in the 19th century also, how were these discoveries publicized or made popular among the population of the United States or the world?
Well, the learned societies put out publications. I mean, there were magazines at the time, that were just like today. You might have there were journals that specialized in scientific subjects, and then others that amongst all the other things they might have, they'd have an article about new theory of fire, or phlogiston is somebody would say phlogiston is still really the right way to explain it all, but so yeah, the Learned Society, the London Society for Advancement of Science, and the Académie des Sciences in Paris were not shy about disseminating their ideas.
So assuming that most people read the newspaper or these news things, that disseminated the information among people who could read.
Right. And you also had That the lecture circuit was very important. You would have traveling, sometimes scientists and others would go from town to town. In this country, we had chautauquas, um, which my mother remembers. She grew up in an upstate New York, and when the Chautauqua came to town, it was all very exciting. They would go to the opera house, and we'd have lectures for the parents, and amusements for the children, and that kind of a.
Thank you.
You know, Jim, I can't help but think this presentation almost should be a requirement of Chemistry 101. You know, really, because we've seen the evolution of thought. And, you know, you could just see in your presentation the periodic table slowly emerging from that. So that's something that struck me immediately. And what's the periodic table's 300 years old, Lavoisier and all. Um,
That was the beginning of it. Yeah, it was a guy named Dalton who first proposed that, and started putting the various elements that were known together in a coherent graph.
and yet, several thousand years ago, the idea of atoms was there. If I remember correctly, that was some Greek or somebody 2,000 years ago plus.
Indeed, well, the Greeks and the similar concepts came up in Buddhist thought, almost as old, maybe even older.
And then somebody else comes up with the idea you mentioned that atoms must have smaller parts too. And we now know we've known that to be true for the last 75 years or whatever. Uh, and I read now in particle physics articles that I understand for a good 5 minutes before I get lost that they've been much talk about something even smaller than quarks and all these and all sorts of elementary particles. And you mentioned where does it end? And we haven't seen the end of it yet.
Right. That was Aristotle's response to the atomists. He said, "If why should it stop at a particular arbitrary point?" But I think isn't the Higgs boson one of the smallest things that they imagine?
It is. It fit into a conceptual theory neatly.
Right, and
But
they've theorized it, but they haven't actually, or they're every once in a while somebody says, "Oh, I found the Higgs boson," and others say, "No, no, 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 you haven't."
well, I believe they did several decades ago,
Oh, really? Okay.
and
All right.
but yeah, so you know, we don't know that there is an end to how small things get.
Mm.
Uh, so
I'm looking forward to a chapter on fire and religion, uh, which I think you have alluded to previously, but also just the use of fire um, within several different religions and the Indian cultures. And um, so, I mean, you can write lots of books on fire, right, Jim?
Yes, but in my book, my presentation today is based on one chapter, and I have actually two chapters on fire gods.
Cool.
I mean, there's gods of the hearth and gods of the forge, and I try to limit, it's such a vast subject. I tried to limit the scope and not talk too much about sun gods, but in some cultures, the distinction is lost. Um, but then there's theophanies, gods who are not fire gods per se, but who or divinities can speak to us through the burning bush or the pillar of fire that leads the Israelites out of Egypt, and
Mhm.
the the Torah is full of theophanies, particularly stories of Moses. But they appear in other cultures as well. There's the story of Semele and the lover of Zeus, and who asked to see him in his fullness, and in Bhagavad Gita we have Krishna revealing his true self to Arjuna, and it's just full of fire imagery. And then there's fire rituals in that are just permeate so many religious practices. Yes.
This is sounding like a presentation for
I think
next year.
Roger's waiting to ask a
Yes,
question.
please.
I'm patient.
Go ahead.
My observation is that if there were to be a test on the rich and complex details of your presentation of one chapter, I would do really very badly. I would probably fail. So I don't have any questions about that. Also, I have the observation that the fire issue over history in culture is so complicated that it's almost impossible to come up with a 2 to 4 word title that encapsulates what it's all about. So I don't have a suggestion on that, but I do want to know about the subtitle. Could you tell me a bit about the burning bush and burning man?
Well, part of my inspiration for writing this book came out of it actually came out of the opportunity to give a sermon at the Unitarian Universalist Church of Berkeley, where I've been a member for many years. And when the ministers go away in the summer, those people in the congregation can step up and take over a service. And I thought, well, what am I going to write about? And having been to Burning Man at that point, I think probably a dozen times, where fire is treated as a spiritual practice in many different ways, I thought, oh, okay, I'll do a sermon about fire and spirituality, and went on Amazon to do my homework and looking for a book on that subject. And to my astonishment, such a book has never been published. And years later, I said, okay, I'll do it myself. And years later, I came across a quote from Toni Morrison, who says, if there's a book that you want to read that doesn't exist yet, you must write it yourself. That's exactly what I did. But I just putting the burning bush, actually, I go back further than the burning bush. I go back, actually, in one of the first chapters talks about the stories of how we came to control fire. And and the myth of Prometheus is just one. Every culture has a story about how it is that we, alone among the animals, have this power. And so that chapter balances the mythology of that and the scientific speculation it has to be about what happened and how it happened and what stages it happened. But it just seemed like a nice framing from, it's pretty far back there, the burning bush, what, 5th century BC or whatever, Moses was supposed to have lived. And then this very recent festival, which I talk about, I have a chapter about fire, the revivals of the fire ritual included, and I talk about Burning Man, and that's where I bring in some of my own experience. So it just seemed to encapsulate two ends of a large time span, and just to suggest that I was covering those two ends and everything in between.
We have any other questions here before we close out? Jim, I heard you talk about several chapters, so it sounds to me like I could be so bold as to ask you to think about making a presentation a year from now on something else, or whenever you want. You're certainly welcome to do that.
Well, the chapters that I've presented are I think are the ones that are most directly about science, and I know that that's your focus, and others get off into. I mean, creatures of fire is, although I do there is actually someone wrote a somewhat tongue-in-cheek article trying to explain scientifically how dragons might be able to breathe fire, but that's pretty much all mythological, and then a lot of it is religion, and then I guess the other chapter this is a chapter about fire in the body, which talks a lot about the humoral system and the Ayurvedic medicine and Chinese medicine and all, and the parallels between how in each of our cells there's a tiny little fire, which is, I mean, we are creatures of very controlled fire, and then the external fire is just combustion is an uncontrolled fire that has no catalyst keeping it in check. But that's that's getting further. Those chapters get further away from science, which I understand to be your focus.
Well, remember the group is called Science and Ideas.
Ideas, okay, that's pretty broad, yeah.
Pretty broad, and the quality of your presentations is such that if you wanted to talk about what the weather's going to be tomorrow, I would probably tune in.
We've had a poet speak to us about creativity, just to give you an idea about the idea angle. So that was fascinating, and we've covered everything in between. So
Okay, all right. Well, I'll think about it. But
I loved your illustrations. Your French pronunciation is excellent. Can't comment on the other, but boy, it's really good, and that's so nice. And also, just the breadth of your knowledge and what you shared with us today is just wow, lots to think about.
I hope it wasn't too much,
No.
Okay.
Roger Pritchard would tell you if it were too much, and he didn't say that, so
It
I'm sure.
wasn't too much.
Right, Roger? You would have let him know.
I just said it wasn't too much. It was.
That's right.
It set me on fire, frankly.
Okay, well, I mean, but by next year, I should be able to point you to places where you can pick up a copy of my opus.
We hope so. That would be awesome.
Yeah, please do. You send it to me, and I will send it out to our world.
We'll have a book signing.
Yeah, absolutely. So with that, I just want to thank you again.
Thanks, Hillary. To you
Wonderful.
too.
Bravo.
I enjoyed it. Okay.
Okay. Thank you very much, and we'll see you all in October when we hear more about vaccines and what's going on with that.